All right. Hi, everybody. Here's question 73 from Chapter 6. This is a straightforward calorimetry question. We get a certain amount of mass of biphenyl that's being combusted in a bomb calorimeter. We get the temperature values with which to find the difference. We're asked to calculate the internal energy and the enthalpy of the reaction for the combustion at 298 K. All right, and we're also given the heat capacity of the calorimeter. Okay, so we start with the internal energy in these questions, right? And we remember the relationship that the amount of heat that's absorbed by the calorimeter is equal to the negative of the heat released in the reaction or consumed in the reaction. Sometimes that happens too. Okay, so let's get on with the calculating here. So heat of the calorimeter is going to be equal to the heat capacity of the calorimeter times the temperature difference, right? Usually written like that. Okay, in this case, our calorimeter capacity is 5.861, and this is kilojoules per degree Celsius, and this is being multiplied by a temperature difference between 419 minus 25.823, both degrees Celsius. Okay, and that gives us a total of 21.076 kilojoules. All right, this is a positive value here, so we see the calorimeter has absorbed 21.076 kilojoules of energy. And that means that the reaction released 21.076 kilojoules of energy. Okay, now so this is equal to this is equal to the change in internal energy, right? We've released this much in the combustion reaction. Okay, now for the enthalpy, hang on, sorry. Oh, goodness. No. Sorry. This needs to be divided by the moles to calculate the internal energy. Excuse me. Okay, so U is the heat of the reaction over the moles consumed. In this case, this biphenyl is C12H10. Okay, so negative 21.076 kilojoules divided by the amount of moles that we have. We got a mass value instead, so this is going to be 0.5141 grams divided by the molecular formula, which is, this is C12H10, so it's 12 times that plus 8 equals 154.2 grams per mole. All right, and our internal energy value then equals negative 6321.57. And now we have the appropriate units of kilojoules per mole. Okay, so that's that bit done. So now for the enthalpy, we need to add to the internal energy also the amount of work required to bring it into existence. That's really what the enthalpy values are describing. And the formula for this is the change in internal energy. I'm not sure what form you'd be seeing this in, but usually he writes it as something like that. Where this is the change in stoichiometry of the gases. So that means that we've got to balance the equation up here, which we didn't do yet. So we have mole biphenyl. Good grief. Biphenyl, which is going to have to react with some amount of oxygen, but that's going to be the last thing we balance. That is going to produce CO2 and H2O. And let's make that 2 a little clearer. There we go. Okay, so 12 carbons. So let's balance that first. We've also got 10 hydrogens. That is a 0. 10 hydrogens, which means we need a 5 here. So that means that the oxygen is this is 24 oxygens plus another 5 oxygens here is 29. This is going to be 29 over 2 to satisfy that requirement there. All right, so that means that because these here are both gas values, sorry, the state matters a lot here. That is a gas value. This here is a solid. We're going to be subtracting the products, which means we've got 17 moles minus 29 over 2. So this is going to be equal to negative 6321.57, right, kilojoules per mole, plus 8.314 joules per mole Kelvin times temperature was 298 Kelvin. And we're also multiplying this by, sorry, I've run out of room here, by our stoichiometry is here. So we have 17 moles in the products minus 29 over 2 is 14.5 in the reactants. Okay, so that right there is our RT ln mu. So 6321.57 kilojoules per mole. We have to do some conversions here because our R value is in joules and not kilojoules. All right, so I'm just going to change that quick. Times 3.5, 2.5. And so we get 6.19393 kilojoules per mole here. Right, Kelvin cancels. This I converted by dividing it by 1,000. This is unitless, so we get kilojoules per mole here. This makes sense if it's like if this is releasing the energy and it's creating more moles of gas than it started with. That means that there has to be some pressure volume work done in order to bring it into existence. So enthalpy should be a smaller value, or should be a more positive value, sorry, than the internal energy is. And this difference here gives us this value here, 6315.38. All right, kilojoules per mole. All right, there you go.